110 attendees. So in the last event, which was in November 2019, 60% of our attendees were graduate students and postdoctoral fellows from 5 universities in Montreal, and the rest were from industry. This is the 7th edition of the Research Boost, and we have amazing speakers. I should thank them for accepting our invitation. We cannot wait to hear about the interesting topics that we are going to talk about. Each talk, we have 3 talks. Each talk will take between 25 to 30 minutes with a few minutes for question and answer. If any of the audience has any questions, please do not turn on your mic and write the question in the chat, and we will read the questions after each talk and may ask you to open your mic if you need any further discussion. So with this, I will introduce our first speaker, Mr. Allan Benchetrit. Allan is a business leader with over 25 years experience in technology firms, including pioneering companies in computer vision, mobile video, and mobile internet. He is the president and CEO of Algolux, a leading company in computer vision, which has received many awards and mentionings, like the most innovative use of artificial intelligence and machine learning in the development of autonomous vehicles and respective technologies in 2020. In 2019, the company was among the IDC top 5 computer vision innovator list. And in 2018, they won the AI Breakthrough Award for computer vision. More about Mr. Allan. From 2008 to 2012, Allan was the president and CEO of Vantrix. From 2004 to 2008, he was the COO of Vantrix, where he served as VP of Sales and Alliances from 2003 to 2004. From 2000 to 2003, he served as VP of Sales Americas for Wisdom, a software pioneer in mobile internet. And between 1993 and 2000, he held sales, marketing, business administration positions at Oracle and HP. So he began his career in 1988 as a software account manager at Dun & Bradstreet. So with this, I will hand it to Mr. Allan to share his screen, and Allan is going to talk about empowering the world's cameras to see the invisible. Welcome, Allan.
Thank you very much for that very warm introduction. It's very nice to be with all of you today. I think that introduction took longer than my presentation, so thank you for that. I think you're going to have to let me share my screen because it says it's disabled right now.
Okay.
So can somebody do that?
Yes, sure. Now it's working. Can you share?
Yes, now it's working. Okay, just a moment. Okay, can everybody see that?
Yeah.
Okay,
yeah.
Great. Okay, great. So per the introduction, we are going to talk a little bit about Algolux today and what our vision is, because even computer vision companies need to have a vision. Our vision is to empower the world's cameras to see the invisible. So I'll start by telling you a little bit about the company, and then we'll get into the heart of the technology and our business. So the company is based in Montreal. We actually came out of a technology incubator called Tandem Launch, which focuses on tech transfers. And we were very lucky to basically bring in the intellectual property that was created by my co-founder, Dr. Felix Heide, who is a German national who completed his PhD at the University of British Columbia, and then went on to do a postdoc at Stanford and is now associate professor of computer vision at Princeton University. So Felix and I are essentially the co-founders, and we've brought together a great team to help us build out the company. Dr. Paul Boucher, who sits in Montreal and is our VP of R&D. Dominic Durante, who's our CFO, is also in Montreal. Dave Tokic is our VP of Marketing, and he works out of our Silicon Valley office. And we've recently made a new hire who will be heading up our business in Europe and Asia. And he will be based out of Germany, and he's going to start with us in January. So as you could see here, we've got our headquarters in Montreal, which is where the vast majority of our employees are. So probably, I guess, somewhere around 85% of the employees are in Montreal. And most of those employees are in R&D, in fields like computer science, imaging, computer vision, and of course, we've got quite a lot of expertise in deep learning and neural networks. And as you could see here, we've done a lot of collaboration with the academic community. Most recently, I think that we presented 6 papers at CVPR, and most of those were in, again, collaboration with various academic institutions, but also with some companies like Daimler. So our mission as a company is to empower vision systems with the most robust perception technology for all conditions. So why is this important? As I will show you, computer vision is a very promising technology. It's already being widely adopted in a number of different areas, but it actually has some very serious limitations around its ability to accurately process in low light and bad weather conditions. And of course, bad weather conditions outside could mean rain and fog and sleet, but even indoors, you could actually have bad ambient conditions like low light, shadows, darkness, smoke, dust, that kind of thing. And so we really believe that these are problems that absolutely need to be solved. And so we've decided that the best place to actually solve those problems is in the automotive industry. For one, there are about 80 million new vehicles that are coming to market every year. And with that, more and more of these cars are going to have computer vision technology in them. In the short term, in the present, we've got technologies like advanced driver assist that basically help us, keep in our lanes, help do detection of our blind spots. There's highway autopilot that basically helps us navigate in highway scenarios. But there's already robotaxis on the road today in very limited scenarios, like operating in retirement communities, as an example. And of course, in the future, there's great promise around the idea that there will be driverless cars very pervasively. That could still be 10, 20 years out before we see it, as a very commonplace type of vehicle. But for sure, there is a future there. Having said all of that, the other reason that we chose automotive is because of the societal impact that this industry is having. Close to 1.5 million people die in road accidents annually, and over 100 people die in road accidents in the US every day. And so, we could have chosen other areas to get into, but certainly would not have had the kind of impact that we think that we can have with the automotive industry. And we believe that mass market vehicles, while they are going to gain more and more technologies in the future, are really going to be reliant on computer vision more than any other technology in order to be able to see their surroundings. And there's 3 main reasons for that. The first is that cameras are low cost, they're small, they're very easy to deploy into the aesthetics of the car, as opposed to, let's say, LiDAR, which sits like a bucket on top of the roof of the car. The second is that computer vision is really the only solution that can do object class detection. In other words, tell the difference between a car, a van, a person, a traffic light. And to go even further than that, it's certainly the only technology that can do detection of the state of the traffic light. In other words, tell the difference between a red light, a yellow light, and a green light. And of course, that's very important when you're feeding into the controls of the vehicle so that the car knows what to do in those scenarios. And then last, but certainly not least, is the fact that there's already cars on the road with 6 to 8 cameras, if you think about a Tesla Model 3 as an example. But we're already seeing designs for vehicles that are going to have 10 or more cameras. And that's mass market vehicles, you know, where we don't have to talk about robo-taxis. And as you could see on the chart on the right, even though radar and LiDAR as forms of perception will certainly find their way into more and more vehicles, these technologies will be greatly outweighed by the number of computer vision cameras that will be going to market for the foreseeable future. So all of that is great, but the problem is that computer vision doesn't actually work very well. So the AAA did a study last year where they took some of the most advanced vehicles that exist in the market today, and they tested them over a long period of time on a test track for their ability to actually meet the requirements that they market to consumers. And so what they were primarily testing was all of these advanced driver technologies, assistance technologies. And of the many conclusions that they came to is the one on the left, which is cameras, which are primarily used for object recognition, as we just discussed, have diminished capacities in low light and other conditions such as rain, snow, and fog. So let me just show you right now some of the results of the trials that they did. So I think you get the picture. The technology is not working very well. And the interesting thing about this is that you really couldn't find a more simple scenario. There's no other obstruction on the road. It's a clear day. There's really no reason for these technologies to be failing the way that they did. And in fact, in all of the testing that they did, the vehicles hit these pedestrians 50% of the time during the daylight, and they actually hit them 100% of the time at night. So basically full failure in evening conditions. So what we are doing to address this problem is we've created an end-to-end deep learning network, which essentially combines the image formation function, which is typically done by something called an image signal processor. And we've combined that with the computer vision detection model into one end-to-end network that basically sits on top of a differentiable image signal processor. And by doing that, we are able to take the input directly off of the sensor to deliver the output, which is not how computer vision works today. Today, computer vision basically has an intermediate step that provides a JPEG as an output, which is then used as input into the computer vision model. And the problem with that approach is that you end up using and training your neural network on highly processed and compressed images. And we believe that it's all of that sensory data that is being lost that leads to these big problems with computer vision output. The other thing that we do as part of this is that we can actually co-train the deep learning network with the camera components. So by training all of these things end to end, we are able to get much more reliable results, as I will show you. So first, as just a before and after type of still image here, is how we compare against some leading neural networks in the market today. So as you could see, the job here is basically to do object class detection and classification. It's a pretty simple use case. And as you could tell with faster RCNN, despite the fact that it's a much more compute-hungry neural network, it misses a lot of the cars that are parked along the side of the road, but it also misses the 2 pedestrians that are on the side of the road. Now, RCNN would have likely worked very, very well during the daytime, but it's in these nighttime type of conditions where you've got glare, you've got shiny road surfaces, you've got glare coming off of the street lights, where the capabilities around these kind of edge cases become greatly diminished. So now that I've shown you some still images, I will show you what really are the 4 of the hardest cases when we speak with the car companies. So dark night, snow flurries, foggy night, and low light and dirty windshield. So I'll just play this one on the top left. And as you could see, we are able to detect all of the objects that the neural network has been trained for, despite the fact that these are pretty challenging conditions. I mean, even for a human driver, it's pretty challenging, right? You've got variable lighting, you've got glare coming off of the wet roads, glare coming off of the oncoming headlights. You've got pedestrians that are lurking in the shadows and trying to jaywalk. There's a lot to deal with here. And yet, as you could see, the vision model is actually doing a really great job. So if I could just kind of fast forward here and show you these other videos, you'll see that even in these other situations, even with different cameras, with different sensors, we're able to do a really good job of detecting all of the various objects that we have trained the neural network for. So that's all good, except that you probably want to know how it compares with the state of the art that's on the road. So of course, Tesla has an autopilot. I think it's questionable whether it really should be marketed that way. But in any case, we leased a Tesla and we broke into the camera and we were able to pull off the raw sensor data. And then we did a comparison of their output versus ours. And this is the result. So as you could see, we're able to detect far more objects in this kind of nighttime rainy conditions. And furthermore, I think one thing that's actually pretty important is the fact that there's a lot of flicker here with the Tesla vision model, which means that they very often are losing sight of the vehicles that are directly in front of them. I'll see if I can just find a frame here. Here's one right here, where they lose sight of that vehicle that's directly in front. So that means that if this car actually was running autopilot and that car directly in front were to brake, you would end up in a pretty catastrophic situation because the car has essentially lost sight of the fact that there is a car in front of it. And to just show you another application of this same technology, what we have done here is we've paired stereo cameras with our vision model in order to create a pseudo LiDAR. So you'll be able to see here that we're basically using the depth sensing from the stereo cameras to be able to essentially detect all of the objects on the road. And again, the whole purpose here is to provide an additional layer of safety for the driver. So we've built out a full vision stack, which basically means that we can combine any of these features together, or they can live standalone as neural networks. And we go from everything from object detection and tracking, like you just saw, to traffic light detection, lane detection, free space detection, and all the way through to object and sensor fusion. And the great thing about the approach is that it's really an open system. So we are really software only, and we can combine with any sensor and also with any camera and any processor. So the way that we come to market, and I'm just wrapping up here, the way that we come to market is with two products. All of the demos I just showed are basically with EOS, our neural network, running inside the camera. So this would be an embedded component within the camera. And for that, you get a great improvement in accuracy. But for companies that we're working with that would like to optimize the accuracy of their existing cameras, in other words, they're not ready to make any architectural changes, they can basically use this Atlas product, which is essentially EOS in the cloud, to get improvement on their existing camera output. So to show you what that looks like in real life, this is what a manually tuned camera would be able to output in the way of computer vision accuracy. This is what you would be able to get through our cloud service. So automatic improvement here through machine learning of various objects that were not detected in the manual approach. And then of course with EOS, a great step up in accuracy, because now we're able to pretty much detect everything in the field of view of the camera. And in terms of how do we go to market, Atlas is serving the automotive sector, and also recently we started to, we've recently signed a contract with a very large player in Silicon Valley to address image quality for laptops. And then with EOS, quite clearly, based on all of the demos I just showed you, we're very much focused on automotive, but that also leads to very similar use cases in smart cities and in other forms of transportation. And that's that.
Thank you very much. So let's see if we have any questions. Yeah, I see one question from Dr. Marius Fokaefs. Can more detected objects actually confuse the smart car? This is the first question. For example, when it detects cars from the other side of the road, can the car be confused into swerving to avoid those cars while there is no danger? In technical terms, is there a risk for overfitting the model? So,
yeah, it's a good question. I mean, I'm certainly not the technical lead in the company, but as far as I understand, based on all of the demos and evaluations that we have gone through, extensive testing on the road with our automotive customers, this has not proven to be an issue to date.
So, Dr. Fokaefs, if you have like any more questions, you can turn on your mic.
No, I'm covered by the answer. Thank you very much. This is a very interesting work. Thank you.
Thank you.
Any other questions from the audience?
Thank you, Allan, for your very interesting talk. I have only one question. At the middle of your talk, you are talking about a case that you're only using the camera and the computer vision couldn't even work properly, in the case that we have a clear weather without any obstacle. So do you have any explanation why this computer vision technique couldn't even perform in case of the clear weather?
Yeah, so I mean, we didn't conduct the study, and so by the way, thank you, Marcia, for your question. So we did not, we did not conduct the study, and all we saw was the results. But I think that we can surmise a couple of things. One, in the cases where the computer vision failed on its own, in other words, where there wasn't fusion with radar, it could very well be that the same architectural problems that I described earlier basically prove that it's just not a reliable way to go to market for object detection. meaning that, yes, it's true that in low light and bad weather, it doesn't work at all, but that doesn't mean that it works really well in good lighting conditions, right? Depending on, you know, the amount of, I guess, the amount of testing that went into those computer vision models by the respective manufacturer. The other thing that it can show potentially is that what broke down was the actual fused approach, right? The fusion between the computer vision model and the other sensors, whether it's radar or otherwise. So in other words, maybe the computer vision model might have detected those objects, but it's the fused approach that actually broke down because, you know, clearly some of those vehicles were outfitted with radar as well. But again, I'm only surmising, as you saw, those are not our videos. They were produced by the AAA, but something clearly went wrong in all of those cases.
Thank you.
Of course.
Yeah, I also have, yeah, there is another question here. Let's read this one and then I'll ask my question. Okay. Object detection is a challenging computer vision task that involves predicting both where the objects are in the image and what type of objects were detected. For a complex kangaroo object, for example, how to detect it.
Yeah, I think that that's a different talk. So, you know, we're very focused on the use cases that you saw there. And no automotive company has ever asked us to detect cars, vans, and kangaroos. We've really been limited to the types of vehicles and objects that you see on the road every day. But certainly I can understand that that would be a very complex scenario. But again, what we're doing is we're focusing on the use cases that are most important to our customers.
Yes, sorry, I forgot to mention that the question was from Mr. Nader Naseri. Yeah, if you have any further questions, you can turn on your mic. Okay, yeah. Yeah, I have a question, like, I think it was slide 7 that you mentioned that you, like the new technology is going to embed the neural network inside the camera and inside the sensor. And that's why, like, many existing technologies and existing companies, they don't want it. They want something like on top of their sensors and all the technologies that they have. So how do you see, like, in coming years, this new technology is going to, like, overcome the market, and this is something that we expect from the autonomous vehicles later, or is there? Yeah.
Okay, yeah, thank you for the question. So maybe that wasn't clear, but we are not running on the sensor. We are integrating with the sensor, but actually running on the CPU or GPU of the camera. So we're actually independent of the sensor, meaning that we could very easily move from one sensor to the next, depending on what our customer wants and what the application is. As an example, you'd obviously use a very different sensor for a backup camera than you would for a surround camera system for parking, as an example. The way that things work today is that you do have an additional hardware component in the camera called an ISP, an image signal processor, and that sometimes will reside with the sensor and housed together. But that is essentially the architecture that we're trying to break away from.
Mm-hmm. Yeah, thank you very much. Yeah, just like because I was thinking about the part that you were saying about the JPEG compression and like the quality of the image that coming from those sensors, and probably with this you have like better resolutions, and this like maybe super resolution algorithms has been already embedded on top of that, and this was the idea.
Mm-hmm.
Yeah. Okay, if our audience, they don't have any other questions, Thank you very much, Allan, for the great talk. We really enjoyed.
Thank you. Thank you for the opportunity.
So our second speaker, Dr. Marius Fokaefs, Assistant Professor at Polytechnique Montreal. Dr. Fokaefs is an Assistant Professor at the Department of Computer and Software Engineering at Polytechnique Montreal. He holds a Bachelor on Computer Science from University of Macedonia, Greece, and a Master and a PhD on Software Engineering from University of Alberta. His research focuses on software maintenance and evolution, DevOps, blockchain and security, IoT, and self-adaptive systems. Dr. Fokaefs' work is funded by National Sciences and Engineering Research Council, MITAX, and Polytechnique Montreal. He is a mentor in the Data Insert Create. So with this, I will hand it to Dr. Fokaefs to talk about self-adaptive software architecture for intelligent systems. Dr. Fokaefs, please.
Thank you very much, Hamidreza, for the introduction, and thank you very much for the invitation. It's also great being here with you. So let me share my screen. Oh, I seem to have the same problem. I don't think I have the right to share. Yeah, I think now it works perfectly fine. Okay, so I hope you can see my screen. So my talk is, it's kind of dispersed, meaning that I will touch upon a couple of things. I warn you that it is fairly academic. It's very research oriented, but hopefully you will find it interesting. So the talk is titled Self-Adaptive Software Architectures for Intelligent System. Already this is a big title, so let's try to break it down a little bit. So I am going to cover three main topics. So we will discuss the example of smart buildings as intelligent systems, and then we will see how we can use self-adaptive mechanisms for such systems, for data-intensive applications to adapt and manage their infrastructure. Then I will talk to you about a contribution I had with a former student of mine on the EMU IoT virtual lab. And I will close with a couple of plans for the future that I'm doing with my current PhD students. Hopefully you will find them interesting and we will have a good discussion. So let's start by looking at smart buildings. So what is a smart building? For a building to become smart, it needs a network of interconnected devices to be integrated with the building. So these devices can include sensors or equipment or different kinds of actuators, and they allow the building to monitor and regulate its state. We can do that for the purpose of improving the living or the working conditions when we talk about commercial buildings, economize its resource consumption like electricity, gas consumption, and so on. And eventually, smart buildings have been associated with also green buildings, whose objective is to reduce their energy footprint. So in an interconnected smart building, we have sensors that allow to monitor several indexes like temperature, luminosity, airflow, or even security. And then we have actuators, which is special equipment that allows us to change the state of the building, like thermostats, for example, to regulate temperature, smart switches and lights, air conditioning, and so on. So somebody could ask, like, how is this a software problem? Actually, is this a software problem? The answer is yes, because a lot of these devices and interconnection that I talked to you about is driven by digitization, and software is in the heart of digitization, which is also the enabler for instrumenting the building. When we say an enabler or allowing this instrumentation, we're actually talking about the communication between sensors and equipment, for example. We're talking about how data is handled and managed, like the ingestion of data from the sensors, the storage and the analysis to create models for the equipment. More recently, we're also talking about intelligent control and reactive systems that are based on artificial intelligence and machine learning models. But we also have more traditional tools like visualizations and management portals for building managers to have a picture about the state of their building. So from the software perspective, one of the most pressing questions about a smart building is how do you actually architect the software for a smart building? So we will see a couple of details and examples to try to answer this question. At the same time, smart buildings are also a big data problem. So I assume you have heard the term big data. We're talking about essentially large amounts of data, which for buildings, it is true that they are being produced, but they also need to be analyzed in order for us to gain control of the building state. We have huge amounts of data when we're talking, especially for orchestrated buildings like universities, for example, or hospitals that have a number of grouped buildings which we have to control either in a centralized or decentralized way. We have a very high emission rate from sensors. For example, we're talking about data per minute, signals per minute, and we can talk about hundreds or thousands of sensors that will send data every minute. There is high demand, especially for infrastructure, when we're talking about analysis and model training. We need a lot of data to be analyzed to give us models about the building's consumption, for example, or the building's conditions. And we also need very high precision when we're talking about predictive control, which is the heart of a smart building. For example, think about a situation where we want a thermostat to change the degree, the temperature in a room by 1 degree, but because the model is off, it changes the thermostat to go to up to 100 degrees. So this is obviously something that can cause big problems. Now, thinking about the size of the problem here, one question that we can think about is how do you architect the data and computation infrastructure for a smart building? So I was involved in a project about smart buildings while I was at York University. So we collaborated with Ryerson University, with the Department of Architectural Design and Mechanical Engineering. In Ryerson at that moment, they had a very new building, which was the Student Learning Center. This was about an 8-story building, which was not exactly designed to be a smart building, but some colleagues from Ryerson University thought that it should have the potential to become a smart building. So the purpose of the Student Learning Center was for students to go and, for example, relax or have meetings or have like something, a floor was, if I remember correctly, something like a business accelerator. So, you know, students would meet and have brainstorming sessions to come up with business ideas and so on. So it was an environment for students to feel relaxed, creative, and productive. So in that sense, the working conditions were very important for the comfort and the productivity of the students. So some of our colleagues thought that it would be a good idea to try to automatically regulate these conditions there. So So what they did is they build a front end for semi-automatic building management. You can see here some of the visualizations. There is a portal to see all the metrics. There are floor plans that are color coded based on the conditions. And what we did in this project was we designed and provided the data and computation infrastructure on the cloud to help support these visualizations and this analysis in the back end. So roughly speaking, this is the architecture we had. So on the left side of your screen, you can see the sensor part. That's the orange part of the architecture. Essentially, every room or every zone, if you see here, bigger rooms are split into zones. They had their own sensors, like for temperature, for pressure, for humidity, for light, and so on. There was a controller, which was a device that gathered all the sensor signals, and that was responsible to send it back to our database or send it directly to be analyzed. Now, in the analysis layer of architecture, we use several technologies like Kafka. Kafka is a message-oriented platform that helps us gather, synchronize, and orchestrate messages from the sensors to the analysis. We used Spark engine for our analysis. Spark is based on the MapReduce model for distributed and efficient analytics for big data. We had different topologies for analytics that would use data as streams or data in batches, depending on the type of the analysis. And in the end of the day, we also had the database. So we designed this backend. And what we also offered was, as I will discuss later, we also offered scalability to control the performance and the reliability of the system in case of high load. You can think about, for example, an exceptionally busy day in the Student Learning Center where you had a lot of students. You needed to have even more frequent signals from the sensors. So that would mean more data, faster analytics, and more accurate analytics. So these fluctuations in the traffic we were able to handle by designing these self-adaptive infrastructures, cloud infrastructures for data-intensive applications. So let's go back to looking at this picture here, this architecture. As you can see, some of the boxes, especially in the analysis in the database, they are they have duplicates of their components, like many Kafka components or many Spark workers or many NoSQL database workers. So this is what we call scalable clusters of infrastructure. And how exactly, what is the benefit of that and how do they work? So imagine that we have this simple three-layer infrastructure. We have our users, our clients, or our sensors sending in their requests, and then we have a scalable cluster. Essentially, this is a set of nodes that has exactly the same functionality. So we can have, for example, we can partition the requests that arrive to be handled in parallel by multiple nodes. So performance management in the cloud right now and the notion of auto-scaling is actually happening after the fact. What does that mean? Let's assume that you have your requests that are arriving and you have two nodes. This could be virtual machines or servers that are hosting your analytics application, and they are serving the incoming requests, and then they're using also a database to interact with respect to data. Now let's assume that at some point during the day or even during the week, so this is the trace of the performance. This could be like the response time, or it could be the CPU consumption or the memory consumption. So you have a level of consumption here. Let's assume that at some point during the day or during the week, you start to get even more requests. For the example about the sensors, that you get more signals. So this would cause your performance to, your resource utilization to increase. Okay, so the red line shows an increased utilization of CPU, for example. So reacting after the fact to regulate performance means that we would add a new server to regulate our performance. So this would drop our performance to the original level. So this management style, this architecture for self-adaptive systems is known as MAPE-K. MAPE-K is actually an acronym that stands for monitoring, where we actually monitor the vitals of our system, like CPU utilization, memory utilization, response time, and so on. Then we have the analysis. The analysis will take this trace and it will say if there is actually a problem, if we need to react to an abnormal situation. And then we have the planning, which actually is how we are going to react to every bad situation. And then we have the execution, which is the actually adding the additional resource. In principle, we also have the knowledge, but in the ex post facto performance management, the knowledge doesn't actually exist like that. So what we did was we extended this MAPE-K loop to actually include a model. So this is our managed system. This is like our smart building infrastructure. You have the requests, you have the replies. This is our monitoring system. And in here we have the analysis part, which is based on a model. So what the model does is we get the new metrics, the new traffic, okay, how many requests we have, and we predict how many additional resources we need in order to get back to our resource utilization goal. And by doing this exercise in the model, by the way, is also self-adaptive. So as it gets new information, it tunes itself. And then we plan for a different action every time this analysis is executed. And then we perform this plan. Now, in this example, without the model, we would react in a static way. So every time the analysis would identify a problem, it would add a static number of new resources. For example, 1 virtual machine or 2 virtual machines at the same time. With the model, so the model represents the knowledge. With the model, what happens is this is our goal. By adding 1 more VM, our model would tell us that we do not have a big change. We cannot attain our goal. But adding a second VM would actually reduce the utilization to what we want it to be. So dynamically, it decides whether it will add 1 or 2 or 3 or more resources. So this model part represents the knowledge. We can say that the knowledge can, the model as a knowledge base has the ability to integrate multiple sources like the infrastructure, the application, the performance indexes, and so on. On the other hand, execution is actually automating the performance management and the infrastructure management. So the combination of integration and automation, you can consider it as a definition of DevOps. I hope that you have heard at least the term DevOps before. I'm not going to expand more on it. If you have more questions at the end, we can discuss it. But for now, you can think that integrating multiple aspects and automating these aspects is the heart of DevOps. So here are some an example of the results we attained on the problem with the Ryerson University building. At this bottom graph, the blue line represents the number of requests our system receives every second. So you can see that the requests are fluctuating. And this green line is the response time. So you can see that with the exception of a few bumps, on average, we have attained a response time of about 1 second per request, which was our initial goal. In order to achieve that, we monitor the CPU utilization of our scalable components like the Spark Analytics and our web workers. Cassandra is the database which was not scalable for a couple of reasons. So as you can see here, our goal was for our CPU not to exceed 80% and not go below 40%. So you can see that we stayed fairly well in this region here, and we achieved that by increasing the number of virtual machines for our scalable components. So this was an example of self-adaptive systems and how they can be applied on the domain of smart buildings, for example. So now I am going to switch pace a little bit. I am going to talk to you about the EMU IoT Virtual Lab. So this came right after we completed our work with the smart building. One problem we had was that while we were working on the smart building project, as I said, the Student Learning Center at Ryerson was not designed to be a smart building, which means that it did not have all the devices, sensors, or equipment to become smart. So we had to experiment with a few resources of our own before we deployed a solution in the building. Unfortunately, what we learned was that smart building sensors and equipment are very hard to come by, especially for even for a large research group. The funding can be a challenging thing in order to acquire this kind of equipment. And we learned that to simulate even one smart building or even more, we may need a very large number of sensors and devices. And the question was, okay, we can buy those. Okay, we may have the funds to buy that, but after the project ends or even after an experiment ends, what will happen to these devices when the experiment is done? We're left with, let's say, 200 or 300 sensors. We can find other projects to do that, and of course we cannot stay with the same devices for 5 or 10 years, right? So it's very inefficient to get the devices just for the research project. Of course, another thing was, to get a day's worth of data from the building requires a full day, but in simulation, we could have simulated a day's worth of data much faster. So that was an incentive for us to go to a simulated solution rather than use the real deployment. So for that reason, we developed the EMU IoT Virtual Lab, which is a simulation environment for IoT networks. It is completely based on Docker technology, on container technology. And at its first version, it was capable of simulating temperature sensors, light sensors, and IoT cameras. So as I said, everything was in a container, and essentially we simulated every hardware device as a Docker image. For those of you that know about Docker, a Docker image is a file that specifies the software that will run in the container. And in this case, our software simulated an IoT device. So it had a few parameters like how often it will emit a signal, how much data it will send, what type of data, and so on. And then we had the container, we had the IoT gateway. The IoT gateway was supposed to simulate a Raspberry Pi. A Raspberry Pi in IoT network serves as a controller. If I go back a few slides, essentially the Raspberry Pi is this controller here. So it gathers the data that the sensor sent. It may do some small transformations, and then it will forward the data back to the cloud. So in MOIT, this is how an IoT virtual network looks like. So you can see that we can simulate a large number of IoT devices, an equally large number of Raspberry Pi gateways, and then all these will send it back to the cloud, to the Kafka node for storing and for pushing to the analytics. And this was also done with containers. So we built this solution. We ran a couple of examples. We powered our research with Ryerson using this network. And at the end of the day, we actually wonder whether this was actually something useful or if it was successful, besides the fact that it helped us actually run our experiments. So we actually tried to put it down and say, how much money would it have us cost if we wanted to do the same experiments with actual devices? So these are a few indicative numbers. You can find the resources in our paper. So it was about $80 for a complex temperature and light sensor. We assumed that we would need a bit more than 300 of those. And an IoT camera would cost a bit more than $200, and we would need about 30 for our experiments. So in order to saturate our backend system. And this was about $34,000, $35,000. Now, when we went back to do our experiments in our simulated environment, for 8 hours of experiment, you can see that it is even less than $2. Okay. So this enables researchers to provide, to test their tools, their methodologies, to provide solutions with minimal cost. Okay, so from that perspective, the ability to virtualize and do all kinds of distractive experiments to the infrastructure without actually affecting the actual building. Remember, this was a university building at Ryerson, so we would not be able to do any real experiments without affecting the occupants. So the simulation environment for this scenario proved to be optimal. So with that, I will move to a few future directions just to pique your interest a bit more. So I described the challenge of a smart building, of its data and computation infrastructure, the problem of maintaining performance, and our ability to conduct experiments and research in a cheap but efficient way. But a building is only the first level of smart. What about smart campuses like hospitals or universities? What even about smart cities? Okay, we're talking about even larger scale of problem, even more data, even more complex analytics. On the other hand, performance is also only one quality for software and for the infrastructure. What about reliability? What about security? And also, what about energy efficiency? Remember that one objective of smart buildings is to reduce their energy footprint. If the computation infrastructure actually contributes negatively to the energy efficiency of the building, then we lose a lot of the benefits we gain by instrumenting the building. So let's try to move our example to the next level. So here in the left, you can see like a pictographic representation of a smart building with all the sensors, the controller, and the database. Now think about it that we have like the University of Montreal campus. Okay, we have a large number of buildings. What we can do is we can split the computation infrastructure in neighborhoods. Okay, so in these neighborhoods, one node, one building would be like a subcore, and it would control the analytics and possibly the data and some notion of control from multiple neighboring buildings. And then we'll have a central node that will manage the entire campus. Now, think of let's concentrate on this neighborhood for our example. And think of the example that this particular building here either has a failure, its computation nodes, or it experiences a larger than normal load. For example, there may be a conference there or something like that. So even more data is being generated. Okay, this will affect the performance of the system as we saw before and its resource utilization. If it's using more resources, it will definitely also affect its natural resource utilization like electricity and gas, and it will affect its energy footprint. So the subcore, as we call it, the head of this neighborhood of buildings, will receive a notification that there is a problem with this node, either performance or reliability problem. It will identify the problem, and it will try to recover. And what it will actually do will be to enlist another building in the neighborhood to take some of the load, or to completely transfer the computation node from this building, if there is a failure, to this building, and be able to recover from this failure. So by thinking about smart buildings in group like that, we can, and using the self-adaptive mechanisms, or at least the same spirit as I described before, you can see the benefit in terms of recovery, or in terms of balancing the load. So in this work, I'm actually doing this with one of my PhD students, Masa Hadian. Our objective is to use clustering to identify peers, to identify the building neighborhoods for problematic buildings. Our objective is to also try to update the clusters dynamically as workload changes. So that would mean self-adaptive clusters. And our main objectives are to balance the workload and energy consumption between peers during peak time, exactly as I showed you, and develop continuous deployment methods to recover and redeploy faulty or overloaded peers. So one challenge for that one is for the subcore node to identify the problem. And then the second challenge is, how do you take the computation from this node and transfer it, redeploy it, and restart it on a healthy node? So these are the research challenges that we're trying to explore in this project. And we're going one level up on the challenge of the smart buildings. So to recap, I spoke to you about how smart buildings can greatly benefit from software architectures and cloud infrastructures, and how also big data and big data analytics can play a big role in such systems. I showed you how self-adaptive systems can help us maintain performance, but not only performance, with high accuracy and great efficiency. I gave you a very, very short introduction about the MOIoT virtual lab, which allows us to conduct experiments in very large scale at a very minimum cost. And for the future plans, we aim at using self-adaptive and DevOps techniques so that we can expand the adaptation problems to greater and more multidimensional problems to further enhance the smart building capabilities. So with that, I think I am on time. I would like to thank you very much for your attention. If you have any questions, I would be more than happy to answer them. Thank you very much.
Thank you very much, Dr. Fokaefs. I see two questions here in the chat. How do you realize stability for such a big data problem? And the other one is about the scalability of the smart systems.
So stability is addressed on one hand with the self-adaptive mechanisms, naturally, okay? This is their main purpose, stability either with respect to performance or with respect to other qualities like security and so on. Now, one that knows a little bit more about adaptation in digital systems will know that the adaptation itself can actually cause instability in some cases. So we have experienced this in many of our problems. In fact, if you read some of the papers that I cite in the slides, we have done a couple of small tweaks and tools to handle stability. For example, especially depending on how small or big is your infrastructure, if you add a new resource, the immediate impact to the performance is very big, and is very visible. For example, if I only have 2 VMs and I add a third one, I can actually drop the utilization even at the half. So if I leave it like that, in the very next iteration, I may be forced to remove this extra VM. And as you can imagine, I can go up and down like that. So just to give you an example, and what happens in real cloud systems like the Amazon EC2, I can actually freeze my self-adaptive system. I can keep monitoring, but for another minute or another 5 minutes, I will make no adaptive action, and I leave the system to settle. This is a very known property in control systems and in signal processing. And actually, the time that it takes for the system to settle after an adaptive action is a known property of controllers. So I hope I answered a little bit the question. What was the second question?
Yeah, the second question was about the scalability of these smart systems. So I think you.
Yeah, so scalability, I just spoke about it. So the natural scalability of the systems obviously has limitations, as we discussed. And I hope I convinced you that we are talking about a big data problem. So we have a lot of sensors, we may have a lot of buildings, we have different types of sensors. So we're also talking about variety of data, volume. The velocity is also an important issue because we can have high emission rate. So scalability is an issue. By using cloud computing and by using scalable infrastructures based on containers, or as I've shown you, NoSQL databases, MapReduce analytics, we can definitely handle the scalability as a problem. Now, what we did with our self-adaptive mechanisms is to go one step further and aid this natural scalability of cloud systems by providing some intelligent management systems to better handle the quality of the software and of the data analytics.
Yeah, thank you very much. Any other questions from the audience? Yeah, we have another question here. For security use, the blockchain, did you use blockchain for the security? If yes, how do you make a connection between AI and blockchain?
Yeah, so this is an interesting question because this is actually another project that I have in my group. I am not mentioning it directly here, but I have another PhD student who is actually doing exactly that. So we are integrating blockchain and IoT. In that example, we're going a little bit smaller on smart homes, not necessarily smart buildings. But what my student and I are trying to do is we're actually trying to scale the blockchain infrastructure itself. We have seen that, especially in IoT, we're still talking about big data, and we want to study the scalability of blockchain against IoT big data. And there are a few adaptive points, action points in blockchain that we can tweak to handle the performance of the blockchain infrastructure. As for the integration with AI, in that case, the AI will be integrated in our self-adaptive mechanism. And as I spoke about the model part, the model is actually the AI part. We are training performance models to capture this hybrid kind of behavior between security and performance and energy consumption on blockchain. And we're using this model predictive control to handle scalability issues in the integration of blockchain and IoT.
Yeah, thank you very much. I hope you got your answer. If there is no other questions, I would like to thank you again, Dr. Fokaefs, for the great talk. And our next speaker, Mr. Chahin Fiouzi, technical expert at Rogers Communication. Mr. Fiouzi is a technical expert at Rogers Communication. He has been with Rogers for 12 years. Before Rogers, he was with Ericsson Canada as a senior software engineer, architect, and manager for over 10 years. He was also a software engineer at Lockheed Martin for 4 years. Mr. Fiouzi has received his master's degree in telecommunication at École Polytechnique, Montreal, He has also another master degree from Université de Paris-Orsay. Thank you very much, Mr. Fiouzi, for accepting our invitation. Mr. Fiouzi is going to talk about the SIM and eSIM on telecom industry. So please share your screen, and it's all.
Yes. Do you hear me right now?
Yes.
Okay, good. I try to share my screen first. Should be this. Share. Guess you see that? I guess so.
Yeah.
Good. Okay. All right. Okay, I'm going to talk about the yeah, it's good. Okay, I'm going to talk about the SIM and eSIM in the telecom industry. I'm working on this subject for, as you said, 12 years. I think there's not too much documents or courses or books that has been written for this SIM and eSIM, and that's why it's good to present that to this audience. It's not. It's basically I'm just more talking about the more practical sides of this SIM and eSIM that we're using day to day at any telecom industry like Rogers, Bell, Telos, and any other MNO. So this presentation basically is talking about the SIM. Like you were talking about the SIM card, you have the SIM cards in the device that when you go to buy a phone, basically they give you a SIM cards, and then the operators over there is just provision your SIM cards. And also I'm going to talk about the eSIM because in the near future, and actually it's happening right now, that there is no more physical SIM cards. It's going to happen. It's going to be everything is going to be as embedded SIM cards. And what is needed in terms of the servers to be able to download these profiles into the SIM cards, inside the phone, which we call that eSIM. So what we have this SIM cards and eSIM, how these, first of all, what are their roles in the telecom industry, and then how we can modify the content of these SIM cards, and there's a lot of information in each of them. And these information has to be changed either dynamically or can be changed statically at the beginning before you get the SIM card. So basically SIM card has its own data, but some of the data inside the SIM cards can be changed dynamically in order for a subscriber to use the overall aspect of the telecoms, what is needed and what we can do as a dynamic modification. Also, I'm going to talk about the eSIM. I think this is better like this. I'll talk about the eSIM. And eSIM, basically, we have many servers that are attached to it. The one that I'm going to describe here is SMDP Plus and SMDP. And at the end, if you guys have any questions, I'm going to be happy to answer. So before starting, there's a couple of definitions that needs to be taken into account, and this is some of them is here, and we're going to talk about the OTA. OTA is an over-the-air activation platform. This platform is used to, as I said, to update the content of the SIM cards or the content of the eSIM. That is a very important platform in terms of the provisioning. Like if this platform is going down for any reason, then the provisioning aspect is not going to happen. And obviously, there's going to be the problem, the provider that it has to be resolved. So this platform has to be very secure. It has to be very reliable, and it plays a very high roles in the telecom industry. Also, I'm going to talk about the SMTP plus. SMTP means that subscriber manager data preparation. Why we have the SMTP and SMTP plus. I'm going to explain about that. What is the difference between SMTP and SMTP plus? Basically, SMTP plus is for consumer side, and SMTP is for machine to machine, like IoT, that has been described just a few minutes ago. We're talking about the SMDS, is a subscriber manager discovery server, and basically this server it's going to be in the future. Let's you have the eSIM, embedded SIM, and this embedded SIM. One of the advantage that we have is that all the devices that we have, we can have many profiles that is coming from a different provider. Let's say you have one from Rogers and one from Bell, Telos, and everything. So this can be simultaneously can be downloaded to the device, and the subscriber can choose which one you're going to use in order to connect to what they want. So today there is no such a thing, but eventually it's going to be happen that there's an SMDS that's going to be exist in the Canada that the subscriber can use that in order to flip the profiles from one side to another side. We're going to talk about the LPA. LPA is a local profile assistance. This LPA is going to be used at the device level in order to decide which profile is going to be used and attached to the network of the provider. EUICC is a secure element that contains one or more subscriber profiles. So when we were talking about the SIM cards, it's basically one of the component that is a secure component that exists in the SIM cards called EUICC. And EUICC, basically E means the embedded, U is a universal, I is integrated, C is a circuit, and other C is the card digital. So I'm going to more talk about those things. And we have also another component called SMSR, is responsible for managing the status of the profile on EUICC. Also, I'm going to talk about that, and it's also responsible to download the profiles to the device. So let's start by EUICC is basically when you have your SIM cards. The SIM cards has a very complex structures inside the SIM cards. First of all, in the SIM cards you have UICC, which is a kind of the operating system that is controlling everything on top of this operating system, which contains the data. Those data that it's also attached with a different technology on the telecom side. So you can have a SIM, you can have USIM, you can have CSIMs, and you can have iSIMs. So depending on where the subscribers to which network is going to be attached, one of these structures is going to be read from the network, or actually it's going to be read from the device, and it's going to be uploaded into the device, and then it's going to be used in order to attach to the network. A part of that is going to be attached to the network, which is this is like a very crucial component. If you don't have that, obviously you cannot connect to the network. These components, it contains lots of informations that may not be used only for attaching to the network, but it's going to be used also to for the personal usage or for the network usage or for let's say the voicemail, for the voicemail component. For example, if you want to use the voicemail, it's going to be reside on these structures. So if you have let's say you have 2G, it's going to be as an eSIM. If you have a 3G LTE, it's going to be in eSIM. If you have a CDMA structures, it's going to be SysIM, and is VoLTE. Everything that is going to be VoLTE and LTE and everything is going to be also in the eSIM. So those are the specific parameters that is going to be used on the different component that is going to be attached to the different component of the on the network, basically. So this is part of the. This is basically when you were talking about the SIM cards, you were talking about all of these things. That this is a basic structure of the SIM cards. So in the SIM cards, there is a file store. Is like a directory on your PCs. You have is exactly the same structure. You have a directory there, and in the SIM cards, you have also under each component that we saw, is that eSIM, SIM, eSIM, and SysIM. You can have different structures, and each different structures, each directory contains a different information. Obviously, these informations all you can find that on the standard, and here you have for one of the example is ICCID, MZ, and MSISTN, which is ICCID basically is a number that you see in the back of your SIM cards. There's a 20 digits, and these is stored also in the eSIM. MZ, exactly the same things. MSISTN is your CTN number, your phone number, basically. It's all stored into these component of the SIM card. And also you have something called authentication key. So when we're going to change the content of the SIM cards, the authentication is very important. So there is a handshake is going to be done between OTA, over-the-air activation server, and the SIM cards. And in order to make sure that we are talking about the right OTA and the right SIM cards, so there's going to be a key that's going to be used in order to encrypt and decrypt the information, so make sure that we're talking about the right person. Let's say if somebody comes and take the SIM cards, and he knows what is the what is the keys are. It has to be this key. Has to be well known in the both sides, in the OTA side and in the SIM cards, in order to handshake and update the content of the SIM cards. So this is one of the security aspect that is we use as very important. When a manufacturer of the SIM cards is providing the SIM cards to the, let's say, provider, basically give this SIM card by a file, and this file is very, very important. Has to be very secured, to be restored on the provider, and has to be very secured, stored also in the OTA, because if somebody knows this authentication key, can go and change the content of the SIM cards and damage everything. So obviously, you have the phone book, you have the voicemail, and you have the all other information like a language preference, P element, that I'm going to talk about those things later on. So when we talk to the SIM cards, as I said, we're going to talk about this aspect through the OTA, and OTA is the responsible of talking with the SIM cards. Basically, we can read the contents of the SIM cards. We can update the content of the SIM cards. We can create a file. So everything that is inside the SIM card, when we were talking about that, the previous slide, let's say ICCID, MZ, MSISTN, like all these elements, we call that file. So all these files can be, we can add more files. We can delete more files, whatever that we don't want it. So also there's going to be KIC, KID, which is the key that is going to be used in order to communicate securely through SMS with the SIM cards. There is a PIN code which is used as a card reader. So when we take these SIM cards and we put it into the card reader in order to know what is the content on the SIM cards, so we need some sort of the PIN code in order to to read the content of the SIM cards. And obviously there is something called TLS PSK. PSK is also used as a HTTP keys that needs to be used in order to establish the channel between HTTP channel between SIM card device and OTA. When we're talking to the SIM cards, we have to talk with a specific language, and this language in the vocabulary of the telecom is APDU. APDU is a kind of the language protocol, if you want, that is used in order to talk to the SIM cards. Is like you can consider that like kind of the TCP/IP structures as header, data sections, and the keys are there in order to know which key has been used, or which decryption has been used, and how we're going to do the encryption and decryption in order to update the contents on the SIM cards. So there's a very specific structure has been used, and this is only the protocol that we use in order to update the content. So when we're talking about the SIM card, we talk about the SIM card profile. So in the SIM card profiles, we have lots of files, as I mentioned. Some of them is used for the network. Some of them is used marketing requirements. Some of them is used for business requirements. For the network, basically these are the most important one. Mobile country code, mobile network code. MZ is an international mobile subscriber identity. Is like your identity of you as part of your devices and how it's connected to the network. So in the many part of the network elements, in order to identify a specific person, they use the MZ. Same thing for other part of the other part of the network. They use ICCID, which is called Integrated Secret Card Identification. Basically, both of them are uniquely identify the SIM cards. Short message service parameters is used for the SMS connectivity, SMSC connectivity. And we have more other parameters like a mailbox number. So when you push on one digit one on your phone, and automatically is dial your voicemail. So this is updated on the SIM cards, and automatically is dial your voicemail. So this is all stored in the SIM cards. And roaming partner list. This one is also, I'm going to talk about that. Basically, the OTA contains, let's say, if you want to go to as a roaming, you roam to another country as a provider. Let's say Rogers, Bell, or Telus, or anybody else like a Videotron. So they have an agreement with the roaming partner, and this roaming partner, those roaming partner list is reside also on the SIM cards. And let's say if your provider has a good relationship with the, let's say, Vodafone in France, so he's going to put as a priority to be connected as a Vodafone in France on the SIM card. So if the subscriber, you as a subscriber, is going to go to France, and you have a lot of network there, obviously your SIM card, your device is going to choose the Vodafone, because it's part of the preferred roaming list on your SIM cards. So now we know what is the SIM card is. In order to know how we can update the content of the SIM cards is a platform called OTA. OTA stands for over-the-air activation. There's a three main functionality of the OTA. First of all, as I said, there's a provisioning SIM cards files that needs to be done. So if you go to the point of sale and you ask for to buy a cell phone, and they're going to give you a SIM cards, and they have to provision the SIM cards with the proper informations that let's say your language preference, your voicemail, your all this information that I just mentioned previously, those has to be provisioned, and this OTA is the responsible one that the point of sale is going to say, okay, this guy is going to be connected with this information, and he sends this information to OTA, and OTA sending to SMSC, and SMSC sending to the SIM cards, and gets the update is going to be done on the SIM cards. So this is the first important role of the OTA. The second role of the OTA is to update the roaming files with a dynamic preferred roaming network, and this is basically is that, again, if you roam to another country, there's a network when you tune with one of the network over there, it's going to talk to our network, let's say your network, your home network, and it's going to say, okay, these guys, if you know this person, and it's basically HLR to HLR, I don't know, home location register platform that is talking to the home location register at your operator, and is going to say that, okay, do you know this person? And then by asking to get the profile, your profile is downloaded to the roaming network, automatically there is a platform that is going to listen to that, and is going to say, okay, this guy has been roamed to France, let's send him the proper on our preferred network. And dynamically this information is coming to the OTA, and OTA sends this information dynamically right away to the subscriber, let's say in France, and automatically, if you're tuned with the different network, that preferred network is going to be changed, and is going to change it to the the preferred network that's in the list that is going to be dictated by OTA to these SIM cards. The another aspect that we have in the OTA is that we can combine the SIM cards. So SIM cards, when we get that at the originally at the one specific times, it contains lots of information, and some of this information is changing around the time, and some of them it's really needs to be combined to the whole SIM cards that we're going to tell them that look, this is from now on, this is the information that you have to use. And it's not part of the provisioning system. It's not part of the roaming system. It's a completely separate things that can be used in order to on the SIM cards in order to update the content of the SIM cards. So these contents is going to be basically can be a security aspect of the SIM cards, can be any other aspect that the business wants to be changed. So the OTA is also, as I said, is delete or add the SIM cards. So let's say we use a SIM card and this SIM card is attached to a specific person. You can add the SIM cards anytime that you want. You can delete that SIM cards because it has been already used. You can update the file content of the SIM card, and OTA also gives you the inventory of the overall SIM cards, that is active or not active. This is a typical OTA architectures. You have the basically this is the OTA talking to SMSC, and SMSC is talking to the MS network, and network's talking to the SIM card. So basically, this is the flow that is used in order to update the content of the SIM cards. We can use the GUI in order to change manipulate the OTA. And also, for sure, the provisioning system, a point of sale, when they're talking to the OTA, they're talking to an interface, an API, and obviously there is if the SMSC want to talk to the specific person, he has to know where it is, which is an HLR. It's going to interrogate HLR, and in order to send information to the SIM cards. Here I mentioned that is SMSC as a point of transport level, and it could be also HTTP. So it's not mentioned here because I use just a picture that is in the internet. But then the reality is that we can have either SMPP message, which is the SMSC language, or we can have the HTTP, which is a data connectivity directly to the SIM card, to the SIM cards and OTA. They use HTTP, and then on the top of the HTTP channels, we send the update of the parameter that needs to be updated. Now we're talking about the eSIM. eSIM, basically, there is a two type of the eSIM exists. Like eSIM, the difference between SIM and eSIM is that, as I specified at the beginning, is that the SIM is a physical, and eSIM is not a physical thing. So there's no more physical SIM card. It's going to be from now on, all the new SIM card devices that you're going to buy, the iPhone that we have, all the iPhone and iWatch that we have, it doesn't have a physical SIM card. So we can connect by your iWatch to the network, and in order to connect to the network, we have to download the profiles to the iWatch. And also the same thing for iPhone. The new iPhone has the eSIM, so the profile is going to be downloaded. So everything that's in the physical SIM cards is going to be downloaded from a server to the device, either iPhone, or iWatch or any other components. That could be also the machine, which is the IoT. So consumer is one side of the eSIM, and M2M and IoT devices are another side of the eSIM. Obviously, if you have the IoT devices, nobody can go and put the SIM cards on it. Or yes, it could be SIM cards on it, but for the future, they're trying to avoid to do a manual intervention and to change the SIM card. So everything's going to be through the eSIM. So again, consumer is going to be, when we talk about the consumer, we're talking about the iPhone, iWatch, and the platform that is responsible to send the profile to those devices is SMTP+, which means that subscriber manager data preparation. And same thing for M2M. It's going to be no interaction with the human. There's not going to be a person that is going to go and change the SIM, change the profiles in order to connect from one side, one provider to another provider. There's no human interaction. It has to be done by a mechanism that is controlled by SMTP, basically. We're going to look at that. So SMTP, this is the architecture's diagram of the SMTP+. SMTP+ is the one that is responsible of, as I said, is for the consumer side. This is a consumer part, like is iWatch, iPhone. So basically, this there's a many interfaces that is used. So basically, this SMTP+, it's talking to the operator, which is Rogers, Telus, Bell, and it get the information from the operator in order to download the profile to the device, which is this device here. Device, as you saw, there's a something component called EUICC. Is the one that is contains the profile. That is all the profiles. The profile that is going to be used is going to be completely downloaded to the EUICC, and this EUICC is going to contain the profile. It could be one or many profiles, and in order for the user to choose which one is going to be used, is use this LPA. That this LPA is going to be through the SIM card, through the device. You can, there's a applet that you can use in order to select which profile you're going to use to connect to the operators. It could be Rogers, could be Fido, could be Telus, whatever you have been downloaded here is operator decide to be which one is going to be connected to the network. We have also SMDS, as I just talked to you about that. This SMDS is the one that is, and in the future is going to control the download of the profiles. But right now, this element does not exist, and it's gonna happen in the probably in the near future. That's a global SMTP plus architectures. So basically, what how it works is that the in order to select a SIM cards or eSIM, basically the subscriber is use a QR code today, and you just scan the QR code, and this is scanning the QR code is going to connect it to a server via Wi-Fi, for example. If you don't have any connectivity at the beginning, because the subscriber, you buy a phone and you don't have the SIM card, so it is not attached to any network. So they can use the Wi-Fi usually. And by scanning the QR code here, he knows that which ICC ID has to go and get it. and it's connected to the server, which is the SMTP plus server, and then it get the profiles, and then it's connected to the network. In the case that you have many profiles, so let's say you have already connected to the routers, and now you want to have a FIDO. So you go and download FIDO profile. Again, can be done either through QR code, or could be done through the server that is going to indicate you that, okay, this is, now you can download this profile, everything is okay, you can do that, and then it just connected to the SMTP server. It's download the profiles, and when it's download the profiles, it's through the LPA, it can decide at which one is going to be connected. So it was connected to the let's say Rogers. Now you want to switch to the FIDO, and after that, it just the connectivity is mentioned, and you have this both connectivity. I mean, there's not, you cannot have two connectivity as far as I understand. There's only one connectivity, network connectivity, that you can have. So it switched from one side to another side. This is a little bit more details of how the thing is working in terms of the let's say iWatch and the phone. So basically, your user is going to go to the point of sale. It's going to ask for, okay, I want to have a smart watch, and it's just per you download the applet, and then it's connect to it pairs smartphone with the smart watch, and in the same times it's talking to MNO. MNO means the provider, let's say Rogers or Bell, and he's going to say that okay, I'm interested to have a profile to be downloaded to my smartwatch, and they decided to do which one has to be, and the talking to the server, MNO talking to the server, saying that, okay, these guys, you want to come and it's going to get these informations, and in the same time, it's going to give us give the QR code. The QR code that MNO is going to give a QR code that associated with that subscribers. And once this is going to be scanned, automatically the device, once this QR code is going to be scanned, automatically this device is going to go to the server. In our case, is SMTP Plus. Download the profiles, and it's going to transfer this profile to the smartwatch. If it's smartwatch itself, also could be happen that it's only this one is going to do the QR code. It's going to read the QR code, and it's going to go and get the from the server. So this is basically is how the flow it works. In terms of the M2M or IoT, the word is a little bit different. It's not exactly the same. The only the major difference is that the SMTP MNO is like the Rogers and or Fido or Bell or whatever, and then dictated to the SMTP that, okay, this subscriber wants to have this ICC-ID, this profile, and this this information is going to be communicated in advance to the SMTP, and SMTP is going to download, in order to download the profile to the device. Like I'm talking about here is M2M. The device should have already a connectivity. So we call that the bootstrap. When the M2M machine is already it has to have a connectivity. It's used at the original power up. It's going to go to the so it's a bootstrap, and it's connected to a network, when the network that has been decided to be done at the first time. And if he's going to go to a specific MNO, this connectivity it's going to be established through a platform called SMSR. SMDP is responsible of defining which profile is going to go, but the SMSR is the responsible of downloading the profile. So all this information of the download the profiles is come from SMDP to SMSR and SMSR to the device. So there is another entity that it was not exist at the consumer level, which is SMSR that is exist on the M2M or IoT machine, IoT devices. The only reason is like this is that there is no way for the machine to select which profile I want to go. And in the consumer level, the human can't decide which profile you want to go, but in the machine, there is no such a thing. So everything has to be dictated to the machine. I don't know if it's I finished the time or no, but I think I'm on time. What else we have here?
Yeah.
Yes.
Okay, you're in the last slide almost. Yeah.
Yeah, I'm done. So this is the reference that I got from this for this to gather all the information. Basically, most of them is coming from the Thales. Some of them is coming from the GSMA platform, and some of them is I just got it from the internet. So hopefully this is you guys you find it interesting, and if you have any question, please go ahead.
Sure. Thank you very much, Mr. Fiouzi. Yes, I see one question here in the chat. IP address availability is a continuous challenge with ever-increasing number of devices. Does eSIM provides any benefit in this regard, like being more scalable with IPv6?
I don't think so. It's related to the IP addresses. eSIM is not related to the IP addresses because once, I mean, SIM or eSIM, once you want to have a connectivity to the network, they are going to get by network and an IP address. And obviously, due to the fact that the IPv4 is very short, it's going to be short. Right now, every device has its IPv6, but I don't think so. There's a correlation between IP address and eSIM, as far as I know.
Okay. Any other questions from the audience? No, if no question, let me ask you another question myself. How OTA can communicate to the user with the HTTP protocol?
Basically, the OTA, it's OTA. Basically, it's in the SIM cards. There is a first of all, there is a as I explained. I don't know if I can go back here. Here, there's a TLS-PS key that is it's in the SIM cards that is going to be used in order to establish the HTTP connectivity from OTA to the device and obviously to the SIM cards. So this TLS-PS key is going to be used as a in order to establish the channel HTTP with the device. And it's like any data connectivity that you're going to have with the, let's say you want to go to the Google. There is an APN in your device, and this APN is going to go to the Google. It's exactly the same thing, but instead of going to the Google, it's going to go to to the, and this is handled by an applet inside the SIM card. That applet is responsible to do the connectivity with the OTA, and is used this TLS-PS key that is already stored in the SIM card in the secure manner, that you can connect it to the OTA, and on top of the obviously HTTP connectivity, you can share the information, and you can get the whatever update that needs to be done on the SIM card through the OTA.
Okay.
I don't know if did I answer your questions?
Yeah, sure. Yeah, I see another question coming. Is it necessary that SMDP and SMSR communicate together for eSIM profile?
SMDP and SMSR, it's only, they are communicating to each other only on the machine to machine. It's only for IoT, and it's nothing. We don't have SMSR on the consumer.
Mm-hmm.
So yes, it's very important, because SMDP and SMSR on the machine to machine or IoT, they have completely different roles. SMDP is responsible of defining the profile, and SMSR is responsible of downloading the profile. So it's two different things. In the world of the consumer, we have only SMDP Plus, which does both. It does selecting the profile, and is also take care of the downloading the profile. So the standard that's related for the machine to machine is a completely two different. Is not exactly the same thing as the standard that associated with the consumer, because the only because of the fact that in the consumer, there is a way that we can decide which profile we're going to use, but it's not, this ability is not exist in the machine to machine. We have to dictate it, these things to the device. So the answer is yes. The SMSR is important for machine to machine, but not for consumer.
Yeah, thank you very much, Mr. Fiouzi, for the great and detailed talk.
You're welcome.
Thank you. So this is, if there was no question from the audience, thank you very much for attending the 7th IEEE Research Boost. On behalf of IEEE Montreal Section and IEEE Industry Relations Committee, I would like to thank our speakers. I think everyone has enjoyed the talks, and also thank you all for joining this event and being present during the talk. I hope that this event has been a good experience for all of you. And also, I would like to thank the organization committee who made this event possible. There was, of course, some differences with our previous editions, and so we all hope that we can pass this pandemic and back to normal and normal events, of course, with networking and refreshments, you know. And if Rafael, if you have anything to add, if not, I can close this event if you're there.
I want to congratulate you on putting this all together. I found it very valuable, and thank you very much for your effort in putting this together.
Yeah, thank you very much.
Before closing the event, if the audience are comfortable to make their video on, so we can take the shutter screen.
Oh yeah, sure.
I really appreciate you.
Thank you.
Yeah, I'm very happy to see all faces.
Yeah, it's better this way, you know.
It takes a lot of bandwidth.
Oh yeah.
Yeah, hopefully we are a small group, so that doesn't make any difficulty.
Yeah.
So if everybody ready, yeah.
Oh yeah.
Ready?
Yeah.
Yeah.
You got it?
Maybe I can try also camera. Perfect.
Okay.
Yeah, thank you all for participation.
Yeah. Thank you very much, and have a wonderful evening. Hope to see you all in our future events.
Thank you.
Thank
Thank
you.
you. Bye.
Bye-bye.
Bye.
Thank you.